Good afternoon, everybody. Welcome to the Samvaad talk by Professor Pradeesha Ashok on frequency allocation and graph coloring. Dr. Ashok has obtained her PhD from the Department of Computer Science and Automation at IISc and completed her postdoctoral research with the Parametric Complexity Group at the Institute of Mathematical Sciences in Chennai. Her research interests are in computational and combinatorial geometry, parameterized complexity, graph theory, and theoretical computer science. Dr. Ashok is specifically interested in designing efficient algorithms for the hard problems in geometry and graph theory. She has published quite extensively at several prestigious venues such as the ACM Transactions on Algorithms and the SIAM Journal of Discrete Mathematics. Dr. Ashok has also been active in contributing to ACM India's efforts and activities related to theoretical computer science through its summer schools. Today's talk is on an important application of frequency allocation in cellular networks, which are heterogeneous networks consisting of two types of nodes, servers and clients. The frequency assignment problem is about assigning frequencies to the servers or base stations so that all clients are within the reception range of any of the servers, but at the same frequency, but receive the same frequency. Dr. Ashok and her team have modeled this problem as a graph coloring problem, thus using graph theoretical constructs to solve a relevant problem in wireless networks. So after Pradeesha, the stage is yours. Thank you.
Good afternoon, everyone. Welcome to the talk. So in this talk, we will be seeing, so the title of the talk is Frequency Allocation and Graph Coloring. So in this talk, we'll see how the frequency allocation problem that is studied in many areas like cellular networks motivated graph coloring problem called the conflict-free coloring problem. And we will, in this talk, we'll see, we'll define the conflict-free coloring problem, and we'll do like a small survey on what are the various results that is known in that field. Also, I'll be presenting some work we have done in this area. Okay. So let's start with the frequency allocation problem that motivated the study of this question. So, okay. So suppose we are in a network which consists of two types of nodes. Let's call them base stations and clients. So we have base stations which transmits at a particular frequency, and we have clients. Okay, and clients are connected to the base station by radio links. So a client will be connected to a particular base station if the client is in the range of that base station. Okay, so it's possible that a client is connected to more than one base station. But having said that, a client will be particularly connected to one base station. Okay, that means the client will be tuning in to the same frequency as that client, as the base station. And so like, for example, this one. So the client here is connected to this base station, which is emitting at a particular frequency. Let's call it red frequency for, okay. And so he'll be receiving signals in that frequency. But if you see the diagram, you can see that a client is also connected to other base stations, which will be again emitting signals at frequency. If any of them are also transmitting in the same frequency as the red frequency, then clearly there is an interference at client's end. So the real communication will be difficult at that. So therefore, one has to make sure that the other base stations that is connected to the client is using different frequencies from the red frequencies. So the problem again is, so given this arrangement of base stations and clients, a client should be, for every client, there should be one base station in his or her, in the range, such that that base station is transmitting signals at a frequency which is not repeated among other base station in the range. Okay. So this is the problem that we have. So the problem is assign frequencies to base station such that every client is connected to a base station with a distinct frequency. Okay, so like if you go back to this, so something like this. So okay, so this is a very simplified diagram of. So here we have used two frequencies, let's say red and green frequencies, and if you check, every client is has some base station in the range whose frequency is not repeated. So any client you see that there is like at most one red or at most one green. So that is true. Okay, and in this, okay, so here I have used two frequencies, but in a complex network, like you might have to use a more number of frequencies. And the goal is to minimize the number of assigned frequencies since the frequency spectrum is limited and costly. So the one objective is to study how to assign frequencies such that the total number of frequencies that you use is minimized. Okay, so we model, actually this problem can be converted to a hypergraph coloring problem. So before that, maybe I'll just briefly say what do I mean by a hypergraph. I'm assuming everybody is familiar with the concept of a graph. So in a graph, you have vertices and edges. So an edge is, in a simple graph, an edge is, it connects to, or we can think of it as a subset that contain exactly two vertices. So here, so AD form an edge and AB form an edge, and so on. Hypergraph is a generalization of this. Again, here we have a set of vertices and an edge, or what you call as a hyperedge in a hypergraph. It is a subset of, it's an arbitrary subset of vertices. Okay, so there is nothing like exactly two. So for example, if you take this, so you have vertices A, B, C, D. So A, D, B, A, the vertices A, D, and B, they form a hyperedge. There may be a hyperedge just containing C, and there is a hyperedge that contains both B and C. So it's a generalization of the simple graphs that we see. Okay, and a coloring of a hypergraph, or a coloring of the vertices of the hypergraph, it can be defined as a function that goes from the set of vertices to a set of colors. So more specifically, a Q vertex coloring is a coloring using Q colors. So I'm just using set 1 to Q to represent the set of colors. So it's a coloring. And now the conflict-free coloring of a hypergraph is a vertex coloring with an added constraint. So a conflict-free coloring means a coloring of the vertex set such that for every hyperedge E, there exists a vertex in that hyperedge such that for every other vertex in the hyperedge U, such that U not equal to V, then the color of U and color of V are not the same in this coloring. Okay. In other words, it's a coloring such that every hyperedge has a distinct color, distinctly colored vertex, or a vertex whose color is not repeated in the hyperedge. So this is the conflict-free coloring problem. So the conflict-free coloring problem was introduced in early 2000s, motivated by the frequency allocation problem in the cellular networks. Okay, so let's. Okay, so this is an example of a conflict-free coloring. So assume this is a hypergraph. The circles represent the vertices, and the closed figures, the polygonal regions, corresponds to the hyperedges. So a coloring like this is a conflict-free coloring. If you take any hyperedge, you can see that there is a there is a vertex whose color is not repeated in the hyperedge. Okay. So this is a conflict-free coloring. Okay. Now, for a given hypergraph, the minimum number of colors required to conflict-free color the hypergraph is called the conflict-free chromatic number of the hypergraph. Okay, so let's go back to this our problem of assigning frequencies to base stations. Okay, so now again to repeat the question, we want to assign frequencies such that for every client in which is connected to at least one base station, there should be a base station emitting at a different frequency, as a unique frequency. So how can we model this as a hypergraph, this situation? So the first step is to, okay, you can think of base stations as points in 2 dimension, okay, and then every base station has a particular range in which it can transmit. So this can be approximated approximately represented by a disk in the plane. Okay, so any point, so or any client that lies within this disk is in the range of this base station. Similarly, you have for every base station there is a disk. So you have, like, if there are n base stations, you have n disks. So we have to build a hypergraph on this. So the vertices of the hypergraph is it's this family of disks. Okay, and what do we need? We need that for every point, or for any point that lies in the union of these disks, there should be a disk. So these are base stations, and we are assigning frequencies to it. So we'll think of a color given to the vertex or color given to the disk as a frequency assigned to the base station. So what is the property we need for any point in that lies in the union of this disks? There should be one disk whose color is not repeated in the other disks that contains the same point. So the hyperedges here. So vertices are the disks, and the hyperedges therefore are defined by the subset of disks that contain a common point. For example, if you take these 3 disks, they form a hyperedge in our hypergraph because there is a common point that is contained in exactly these 3 disks. So you can notice that if you take any subset of these 3 disks, like you take any 2 of them or any one of them, that is also a hyperedge. Okay, right? Similarly, if you take this, okay, these 3 disks again form another hyperedge because there is a common point containing exactly these disks. So out of these 3 disks, you have to color them such that one of them should be a unique color or a distinct color. Okay, so right. So this was the problem that was first studied with respect to the conflict-free coloring of hypergraphs, or let's say that the disk conflict-free coloring of disk is the first problem that was studied in the area of free coloring. So the question is, given a collection of disks, and you need a coloring such that for every point in the union of disk, there is a color I, such that the number of disks that contains and that is colored I is exactly 1. Okay? Or in other words, the color I is used exactly 1 that contain X. So for this problem, the first set of problems, the first set of questions that were studied is how many colors are needed to color. So the general question was for given or for any arrangement of disks in the plane, what is the minimum number of colors needed? Okay, such that any arrangement can be conflict-free colored like this. And so this problem, okay. So in 2002-3, okay, around 2002 and 3, even Lotker and Smorodinsky came up with this result that a family of n disks can be conflict-free colored using log n colors. So if you go back to the frequency allocation question, it says that if there is like n base stations, you have to you can always assign using log n frequencies in a conflict-free fashion. In fact, this bound of log n colors, they generalize to a number of hypergraphs, like hypergraphs defined by half spaces and centrally symmetric objects, and like a much larger class than disks. Another interesting result came later in 2006, that again for the same type of hypergraphs with n disks, but with the extra property that n disk, so we have a collection of n disks such that any disk intersect at most k other disks. Okay, in that case, the number of colors needed to conflict-free color that arrangement can upper bounded by log cube k colors. This is an interesting result, I think, in practical situation also, because you can imagine in a practical communication network, the number of intersection can be bounded independent of n. And therefore, the number of frequencies or number of colors you use can also be bounded independent of n. So this result was given by Allen and Smorodinsky in 2006. Also, related to the disk problem, and dual problem was studied. So remember, so for the last problem, we considered the hypergraph. We considered the disk as vertices, and the hyperedges were defined by points, that the disk containing a particular point. In the dual problem, we can consider points. So you have a discrete set of points as the vertices, and the hyperedges is given by, or is defined by disks. So all the points, so given a set of points and arrangement of disks, the vertices are the points, and the hyperedges are basically defined by the disks. That is, all the points that is contained in a particular disk is will form a hyperedge, and you want to color the points. So again, you can think of problems where the disks are defined, or the disks correspond to a client and points correspond to the base station. Okay. So again, a conflict-free coloring of points will look something like that. So every disk contains a color which is in the disk. Okay. So even for this dual problem, Sariel Harpeled and Shakasmorodinsky in 2005, they proved that even in this dual problem, log n colors suffice. So many of these problems were also the bounds were also tight, means that there are arrangements which needs these many problems. So the another of graphs which I studied was defined by axis parallel rectangles. Again, you are given a set of points as vertices, and axis parallel rectangles define the hyperedges. All the points contained in a particular axis parallel rectangle will give you a hyperedge, and you want to cut the points such that every rectangle contains one point which is with a color. Okay, and here in 2007, it was shown that n to the power 0.382 colors suffice for axis parallel rectangle. So to the best of my knowledge, this is not like a tight bound. The lower bound is much smaller than this, and there's like a gap between the upper bound and lower bound. It's an open question for some time now, right? And also around this time, apart from the practical interest, and also the theoretical interest, there were a lot of connections made between the conflict-free coloring problem and other problems in the other problems being studied in this area. So, for example, this conflict-free coloring of axis parallel rectangles was also interesting because it has links to link to another very important problem in computational geometry called the maximum independent set problem of rectangles. So a bound for this problem will imply some result, will imply good approximation algorithm for the maximum, or good bounds for the maximum independent set problem. Therefore, it is okay. So that's like another motivation for studying this problem. Of course, the theoretical interest is also motivation. Okay, so this was like some of the studies with respect to the geometric hypergraphs or hypergraphs defined by geometric objects. And Okay, so later, I think early around 2010 or so, there was another set of hypergraphs which was studied for conflict-free coloring, motivated by its applications in robotics. So here, so let's consider, okay. So let's consider a polygonal region, a polygon which has, let's say, n vertices, and a robot which moves inside the polygonal region. Okay? And the robot is able to move inside the polygon, and it is needed that the robot is to be monitored or connected to a sensor at any point. Okay, so you want to place the sensors such that at any point inside the polygon, the robot will be able to connect to at least one sensor. So when do we say that a robot can be connected to a sensor? That we can define it as saying that when the robot is in the line of sight of the sensor, or other words, like the line segment joining them, or is completely inside the polygonal region without no walls coming into it. So, okay, so the first problem is to place sensors such that the robot can be controlled from anywhere in the polygon. And actually this problem is the very classic problem in computational geometry called the art gallery problem, to how to find the sensor location so that it is the robot can be controlled from anywhere. Now if you add the frequency assignment element to it, so again we need the same property as before. Like so let's say that, okay, we have placed sensors here, and for example, if the robot is here, there is like exactly one sensor that lies in the range of the robot. Okay, or robot lies in the range of exactly one sensor, and in whichever frequency it emits, it's fine. The robot can be connected to it. But suppose the robot is in a position in which is in the line of sight of different more than one sensor. Therefore, again, it is needed that the robot should be able to connect to exactly one sensor which is emitting at a unique frequency. So this gives you the colorful or the chromatic art gallery problem, in which you will color the guard set, and what the property you need is, again, the guard should be colored such that for every point inside the polygon there should be a unique colored or distinct colored sensor which can see the robot. So this is the conflict-free art gallery problem. So art gallery problem, as I said, given a polygon P with n vertices, find a guard set. By guard set, I mean the positions from that can guard or that can see the entire polygon. Find a guard set that every point in P is seen by at least one guard. So art gallery problem is like a very old classic problem. It's been around from 70s. It was introduced in 73 and it's still studied. Okay. And the conflict-free art gallery problem is looking for a guard set such that every point in P is seen by at least one guard of unique color or distinct color. So this was the conflict-free art gallery problem. And again, the first set of questions that were studied was how many frequencies are needed. And you're trying to minimize the number of frequencies. So in Bachi and Suri 2014 showed that for a subclass of polygons called the orthogonal polygons, and also for monotone polygons, like orthogonal polygons means the polygons with the vertical and horizontal edges, and monotone means it's like monotone in some direction. Okay, so for this set of polygons, log n colors are enough. And later, Bachi, Suri, and Ghosh, they extended this result for all simple polygons. So log n colors suffice for all simple polygons. Okay. Okay. So that was conflict-free art gallery problem, the bounds needed. And another set of hypergraphs which was studied for conflict-free coloring was based on graph neighborhoods. So here I mean the simple graphs. And so that means we given a graph, the hypergraph is defined by, the hypergraph contains vertices of this graph as vertices, and the hyperedges are defined by neighborhood of a vertex. So what do I mean by neighborhood of a vertex is like, okay, given a graph, and you are okay. So the neighborhood of this vertex is is a set of vertices which has an edge, which is connected to this graph with an edge. Like for example, this is the neighborhood of this vertex. So all these vertices, they will form a neighborhood, and they will form a hyperedge in the corresponding hypergraph defined by the neighborhood. So again, there is a theoretical interest, and also in practically you can think of it's a lenient, more lenient version of visualizing the cellular network, the connections between base stations and clients. Okay. So again, conflict-free coloring means a coloring of a set of vertices such that every vertex is uniquely colored, has a uniquely colored vertex in its neighborhood. Okay. So for example, this. Okay, so given a graph, you can color such that for every vertex, there is a vertex of color which is not repeated in its neighborhood again. Okay. Okay, so this is okay. So this is a coloring of all vertices. Actually, you can ask this problem when you are actually you can use it for ask it for any hypergraphs. But especially in graphs, this question was studied a lot. That what if you are only coloring a subset of vertices, and you still have the property that you color only a subset of vertices such that every vertex has a vertex of unique color in its neighborhood. Okay, so again, this question makes sense. Yeah, because so uncolored vertices, they correspond to base stations which are not needed in some way, or some dominating entity which is not needed. So, right. And again, the bounds question, the questions are not very different when you're coloring coloring all the vertices and coloring a subset of vertices. It can be seen that the bounds, the number of colors needed differs by at most one. Like for example, if you take the subset of vertices, you can take the uncolored vertices as one more color, as a color white or something. So if you can color a subset of vertices using 3 colors, then you can color all vertices using 4 colors. That's okay. So again, with respect to graph neighborhoods, the problem researchers have looked at the questions, how many colors are needed. And in 2009, Pak and Tadosh showed that log square n colors. So if you're working with a graph of n vertices, a simple graph with n vertices, log square n colors are sufficient. So again, extending the result, a very interesting result was published in 2017 by a set of authors. They studied the conflict-free coloring on graph neighborhoods for planar graphs. So planar graphs are those graphs which can be drawn in the plane such that their edges do not intersect. So they are kind of sparse in some way. So the interesting result here is we need only 3 colors to color any planar graph. So it's not only a function independent of n, it's a constant function. Okay, so you need only 3 colors to color a planar graph in a conflict-free fashion. This is a very interesting result. And also they kind of, actually they prove a more general result, which might be, which is interested in the graph theory community. Okay, so the result they prove is that if a graph does not contain a complete graph of, or a clique, a complete subgraph of size k plus 2, then it can be colored using k colors. This is the result that they proved. So this is also like, there is a theoretical interest in the graph theory community, because this is somewhat similar to a very open problem in graph theory. So when you think of the proper coloring of proper coloring question in for simple graphs, there is this conjecture called Hardwicker's conjecture, which has been like a very important open problem in the field of graph theory. Like so can we prove, okay, the conjecture goes like, if the graph does not contain a kk as a complete graph of size k as a minor, then it can be proper colored using k colors, and only some special cases are proved. for this conjecture. The conjecture, like for general graphs, it's still open. So what Abel et al. They proved is like a conflict-free variant of the Hardwicker's conjecture. Okay, so that also like it's make this result very interesting. So because of the general results, actually you can prove this kind of results for a large number of like large subclass or different graphs also. Like for example, outer planar graph, you can show that 2 colors suffice. And so there's like a set of results that apply, like that come as a corollary of their more general theorem. Okay, but okay, so planar graph. So after this, again, the researchers were studying what are the different types of, what are the other classes of graphs for which we can come up with good upper bounds. Okay. And Fekete and Keldenich, they proved that 6 colors suffice for unit disk graphs. So unit disk graphs are not planar graphs; they can be like very dense graphs also, but so they prove that 6 colors suffice. So maybe I should say something about unit disk graphs. So unit disk graphs is again it's a geometric graph that was well studied, and one reason for that being popular is that it has a lot of applications in this communication network kind of area.
So for a unit disk graphs corresponding to every vertex, there exists a disk of radius 1, and there exists for every edge the corresponding unit disk intersect. There are multiple definitions which are equivalent for unit disk graphs. For example, we can also represent them as points. So every vertex correspond to a point in the plane, and there exists an edge if the corresponding points are at a Euclidean distance at most 1. According to Fekete and Keldenich result, any unit disk graph can be conflict-free colored using at most 6 colors. For example, this unit disk graph can be colored using 2 colors. So the next set of questions that we study for conflict-free coloring problem is about the algorithmic variant of the problem. So far we were discussing combinatorial bounds on the minimum number of colors needed to conflict-free color a hypergraph of a particular type. So we were trying to get lower bound and upper bounds on the minimum number of colors needed to conflict-free color a hypergraph, or to conflict-free color any hypergraph of a particular type. In the algorithmic version, we try to optimize the number of colors used for a given hypergraph. So recall that the minimum number of colors required to conflict-free color the vertices of a given hypergraph H is called the conflict-free chromatic number of H. And for a given hypergraph, the minimum conflict-free coloring problem refers to computing the value of the conflict-free chromatic number of H. So we will discuss this problem now.
So these are some of the hypergraphs that we have seen, for which we have shown bounds. Okay, and researchers have looked at the algorithmic problem for this, and yeah, sadly, all of them are, most of them are almost all of them are proved to be NP hard problems. Now we know that NP hardness is not not good news for algorithmists, because NP hardness usually implies that or NP hard problem, you don't expect a polynomial time algorithm, because polynomial time algorithm for NP hardness implies P equal to NP, and the conjecture is that P not equal to NP. So therefore, you don't expect polynomial time algorithm for any of these hyper graphs. So if you want to, that means unless P equal to NP, if you want to prove this in the optimum way, or you want to prove this in the exact way, you have to spend exponential time. Okay, so assuming P not equal to NP. Okay, so right. So now when it comes to a lot of my work, our work involves designing exponential time algorithm for the conflict-free coloring problem. So to explain that, I should take a slight detour and tell about the approach that we are using. So we are trying to design parameterized algorithms for this problem. Now, what do I mean by parameterized algorithm is this. So parameterized complexity is like a design a paradigm that was introduced to work on NP-hard problems. So okay. So when you think of a parameterized version of a problem, usually when you think of a problem in algorithmics, you're given a problem with you're given an input instance, and you work on the input instance and give a outer output. And the running time of the algorithm is measured in the size of the input. Now, whereas in a parameterized problem, there is an input. Also, there is a parameter which is supplied to you. Okay? And the parameter can be like a property of the input or a property of the output. But the intuition is that you are choosing a parameter such that it is small with respect to the input, or at least in some cases it is small with respect to the input. Okay, and given an parameterized instance of the problem, okay, let's say I comma k, I is the input instance and k is the parameter. It is said to be fixed parameter tractable, or equivalently there is an FPT algorithm to solve that parameterized problem if the algorithm if there exists an algorithm that solves it exactly, and the algorithm runs in time a polynomial time in the size of input, that is kernelty of I in order of 1, and f of k. F of k is a function which depends only on the parameter, and it's independent of n. Okay, so f can be an exponential function also. Like if you are working with an NP-hard problem, it will be like you have to expect it to be exponential, because you cannot have it like a fully polynomial time. Okay, but what we are doing here is, so even though it's an exponential time algorithm, we are confining the exponential factor to the parameter. Okay. So such problems are called are said to admit an FPT algorithm with a given parameter, and also there is a set of believed to be intractable problems for FPT also. They are called W-hard problems. So W-hard problems under your complexity theoretic assumptions, they don't give FPT algorithms. Okay, right. Now again, okay. So now again, like so what do I mean by an FPT running time here is, so let's say that I'm working with an instance with input size n and a parameter k. So something like this, so 2 power k n square, this is an FPT running time, because I have a function which depends only on k, that is exponential, it's fine. And whereas the function with respect to n square, that's only polynomial. Okay, and these two are not FPT running times, 2 power k, 3 power n, because it's exponential in n, therefore it is not polynomial. And also n power k, that's also because you have a function which depends on both n and k. Okay, fine. Okay, so again, if you look at the FPT running time, the idea is, as I said, we are confining the combinatorial expression to the parameter k. We have an exponential factor, but it is not it's not exponential in n. So intuitively, when you are working with instances with size n and parameter k, such that k is very, very smaller than n, this is like the FPT running time is a good running time, right? Like, so if you have an f of k and k is like the very good case, like k is a constant, then f of k is also a constant, we have a polynomial time running time. Okay, or let's say that k is a parameter which grows very slowly with respect to n, then again it's a good one. Like so for example, if you compare this 2 power k n square and 2 power k, like 3 power n, both are exponential, but one is exponential in k, one is exponential in n, and when n, anyway you have to expect n to be large, right? So therefore it's not. You might ask, or one might ask, like what about n power k? Like when k is small, n power k is also looks like a good running time, then why are we not calling it an FPT running time? So but again, like even when k is small, it is like an exponent of n. Oh, okay, so maybe to just give you an idea, I have some numbers. Okay, so suppose we are working with some instance which input size is 1000 and k, the parameter is 20, and we have this running time 2 power n power k and 2 power k times n. Okay, so 2 power n will translate to around 10 to the power 301 instructions, which will take, so assuming let's say that you are you're carrying out 2 to the power 36 instructions per second. This algorithm in 2 power n with this value of n and k, it will take 10 to the power 282 years to run. Similarly, n power k algorithm will take 10 to the power 41 years to run. Whereas a 2 power k times n algorithm, although it's an exponential time algorithm, will run in 0.01526 seconds. Okay, so this is like motivation of why studying FPT, right? So even though you say that it is exponential, they are like, if you can say, it's like good exponential, like it's exponential time, but it's like better exponential than this. Okay, so that's why we are studying the FPT running times. Okay. Okay, so now let's see some of the work we have done as part of the conflict-free coloring. So most of the work involves parameterized complexity of the minimum conflict-free coloring problem. So the first set of problems that I want to mention is the conflict-free art gallery problem. So this was a joint work with Meghna and Reddy a couple of years back. And here we study the conflict-free art gallery problem, the conflict-free variant. And to the best of our knowledge, this was the first algorithmic study of that conflict-free art gallery problem. And we were able to prove that the problem is not, I should say it's not very surprising, it was expected, but again, we are able to theoretically state that, okay, this is simply hard. And when you come to parameterized complexity, when the parameter is the number of colors used, we can show that it's W hard. Actually, in fact, we show that it's something harder than W hard. But okay, but anyway, it implies W hardness also. But we are able to come up with better algorithms and bounds for special type of, for the art gallery problem, when the polygons are a special type of polygon called 1.5 dimensional terrains. Among other polygons, we also looked at some orthogonal special polygons. Okay, and yeah, so I'm not going into the proofs or the details of how this was proved. This work was presented at the Frontiers of Algorithms conference, Sanya, China in 2019. Okay, so maybe I'll just move to the next class. Okay, so the next set of questions that we studied was the conflict-free dominating set problem. This is a variant of conflict-free coloring problem. This was joint work with Ratin Bhargava, Naman Gupta, Muhammad Khalid Udayagiri, and Dolly Yadav. So here, the variant that we are studying is, okay, it's called conflict-free dominating set. So we studied this for graph neighborhoods, basically. So the conflict-free dominating set question asks this. It's kind of like optimizing the solution in 2 levels kind of question. So far we were asking the question, given a hypergraph, can you color it using k colors? Okay, or what is the equivalently, what is the minimum number of colors needed? We are trying to optimizing the number of colors. In conflict-free dominating set, it asks something more to it. It says like, can you color it using q colors? Also, if it is q colorable or k colorable, what is the minimum number of vertices that needs to be colored? Okay, so that it is conflict-free dominated using q colors. So we are optimizing the number of colors. Also, after that, we are optimizing the number of colored vertices, the vertices that needs to be colored. Okay, I think I should say that, like, this is like, if you want to think about in terms of cellular networks, then again you are minimizing the frequency, minimizing the number of base stations you have to build. Okay, so this is the question, and the question was introduced in 2017 by a set of authors in their paper, Abel, Eric Demin, and a lot of like 7 or 8 authors. So they studied it for planar graphs and proved some hardness results approximation algorithms and etc. Okay, so this is a problem, minimize the number of colored vertices when the number of colors is fixed. And we study the problem for hypergraphs defined by graph neighborhood. So we will we studied this problem for the general graphs, which will include all simple graphs, and we studied the FPT, the parameterized complexity, using the parameter tree width of the graph. Okay, so for tree width, okay, so for the sake of completeness, I will state the definition of tree width. It's okay, you don't need the, even if you are not following it, it's fine. It's not much needed. So let's see. So given a simple graph G, the tree decomposition of the graph corresponds to decomposing the graph in the form of a tree, where then every node of a tree correspond to a subset of vertex of G. Okay, and also it has this three properties that every vertex of the graph is contained in at least one bag. Okay, bag is the node of the tree. So every vertex goes to at least one node in the tree. Also, every edge, for every edge in the graph, they coexist in at least one bag. They appear together in at least one bag. Also, the third condition, for every vertex, the nodes containing all the bags, all the nodes containing that vertex V will form a connected subtree of the tree decomposition. If you have a decomposition with this property, it's called a tree decomposition. And the width of the tree decomposition is maximum size of any bag in the tree decomposition, and tree width of the graph is the minimum possible width for any tree decomposition of the graph. So this is a definition. It might look a little artificial at first, but but again, tree width is important because it's related to a lot of other parameters of the graph. For example, small tree width implies small vertex separators, and also the vertex cover, the coloring number, the chromatic number, all can be bounded by tree width. Just to tell the relevance of using tree width as a parameter, okay, I can also say that, or one practical way of saying that studying tree width as a parameter makes sense, because it's been observed that a lot of graphs which appear in the real world scenario, they have very small tree width. So I will refer to this recent study, which is an experimental study of tree width of real world graph. So this is like one of the papers where this kind of problems are studied. So they have studied a number of real world graphs from different areas, like infrastructure graphs, graphs corresponding to social networks, graphs corresponding to web communication, and so on. And the experimental study has shown that in many cases, the tree width of the graph is very small compared to the size of the graph. For example, if you look at infrastructure graph, the nodes, like there are millions of nodes, whereas the tree width is like small, like it's somewhere between 5 and a few hundreds at most. And but social networks tree width is larger, understandably, but still it is compared to the size of the network, size of the graph, it is small. Again, areas like communication give you graph with a small tree width. So it makes the study of tree width as a parameter relevant, because might be useful for graphs, real world graphs. Okay, so here again the question is, given a graph with a tree width T, find a Confiscate coloring of the graph that minimize with let's say some Q colors that minimizes the number of colored vertices. Okay, so this here we prove this. Okay, we show that there exists an algorithm Q to the power T times N, which is an FPT with respect to T. Okay, and this we were able to show that this running time is also optimal, assuming some standard complexity theoretic assumptions. That means, so we use standard techniques in lower bound construction from fine-grained complexity analysis to show that this running time is also optimal. Okay, so this part parts of this work was submitted or was presented at the Conference of Algorithms and Discrete and Applied Mathematics earlier this year in February 2020. Okay, and this next set of work we have done is so it's called the max conflict free coloring problem, not a dominating set problem. Okay, so this was a joint work with Aditi Dudeja, Sudeshna Kole, and Saket Saurabh. So here, okay, so this is this problem asks this question. So the question that we were asking is, can we, given a hypergraph, can we conflict free color it using Q colors? Okay, so what if it is not conflict free colorable using Q colors? What can we do next? So this problem is pertains to that case where when a graph is not conflict free colorable using Q colors, then what is the best we can do, right? Like so of course we cannot conflict free color every hyperedge using Q colors, but can we maximize the number of can we maximize the number of hyperedges that can be conflict free colored using this number of the fixed number of frequencies we have, or the fixed number of colors we have? Okay, so here again this problem is NP hard, right? So this was the question. When the number of available colors is less than the conflict free chromatic number, want to maximize the number of hyperedges that are conflict free covered. And so we study the parameterized complexity of this question. This question is again NP hard. So so the question is, does there exist a set of at least k hyperedges that can be conflict free colored using R colors? So we are assuming R as a constant here. So here the parameter is k, the number of hyperedges that needs to be conflict free colored. And here first we'll show, okay, so we are able to prove that this problem is in FPT. There exists an FPT algorithm to solve this problem. Also, in the algorithm, the first step of the algorithm is that is, for a hypergraph, we can pre-process the hypergraph in polynomial time to get an equivalent hypergraph whose size depends only on k. Okay, whose size is independent of the size of the actual input instance. Let's call it n. Okay, so it's independent of n, but this after pre-processing we get a hypergraph with whose size depends only on k, or specifically we get a hypergraph with 4 power k vertices and k log k hyperedges. So this is called a kernel in the area of fixed parameter tractability. So first we design a kernel in polynomial time. So actually the kernelization procedure itself give you a direct FPT algorithm. So if you use a brute force approach on the kernel, you will get like an algorithm which runs in R power 4 power k time. But using further techniques like called color coding technique in FPT, we are able to design an FPT algorithm which will run in 2 to the power k log k plus k log R time. Okay. Okay, so this is the result that we are able to prove. And okay, so this result, this work was published in Siam Journal of Discrete Mathematics a couple of years before. Okay, so that by that I come to the end of the work, the conflict free coloring, and some work we have done as part of this. And okay, so what are the further questions that we are interested in is, one is identify more parameters that give efficient algorithms. Like to continue with FPT algorithms, what are the different other parameters that are meaningful to study the conflict free coloring problem? And also we are working on a stronger version of conflict free coloring, and like kind of we would ideally like to do like a contrast, a study of contrast between the stronger version and the conflict free coloring version. And also what are like the conflict free coloring for other graphs, other geometric graphs, or geometric or otherwise. So yeah, I will be like interested to hear from colleagues working in areas like robotics or networks, cellular networks, and others, or web networks, who can like point me to interest of graphs for which the conflict coloring can be studied. Okay, so that was my talk. Thank you for your attention.
Thank you, Pradeesha. Round of applause. Are there any questions? The floor is open. Okay, there's a question in the chat. Ma'am, in the cellular network example, how much harder will it become if we have a limit on number of devices that can be connected to a base station?
Okay, to the best of my knowledge, this problem is not studied. But yeah, so this is like a capacitated dominating kind of question. So yeah, I think it will be interesting to see this. So if we have this also, yeah. So I don't think this problem is studied. So it's yeah. So algorithmically, I'm sure that it is hard. Now, yeah, and also that is, I think that's an interesting parameter that can be asked about. Yes. So I don't think this problem is studied.
So I have a question, Pradeesha. So these are largely planar graphs, right? Are there any other kind of like non-planar
No,
graphs?
planar. So we are not assumed any planarity for
Okay.
in our
Okay.
hypergraphs. No, the graphs we have studied. The hypergraph example, it works for any graphs.
Okay.
That question. And the tree width also it works. It was for a general set of graphs.
Okay.
So planar graph, yeah, it contains planar graph.
Mm-hmm.
It contains a lot of other graphs also. And yeah, even the earlier question, no, we are not assuming any planarity. Only the three colors result, which was given by Abel and Eric Domain and others, that they studied for planar graphs. Whereas the other graphs, like for example, unit disk graphs, need not be planar at all. But even for them, we have better results.
Okay. Okay. Srinivas has a question here. I'll let him ask, and then yeah, I'll come back to some more questions once. Yeah, Srinath, you can ask.
Okay.
Hi, thanks for an interesting talk. I have a couple of questions. One, you mentioned about this 2017 paper about tree coloring. So, so is it does it override? So earlier till now, the four color.
Sorry, I didn't hear you. Which paper are you referring to?
So the three color paper for planar.
Oh yes, yes. The Abel and all.
Yeah. So, so basically, it is an improvement on the four color theorem. Is it? It's earlier a four color theorem for planar graphs. You need maximum of four colors and so on.
Yeah, it is similar. It is something corresponding to. That's what I said. The Hardwicker's conjecture. So the four color theorem is the Hardwicker's conjecture for equal to 4, right? So so this is like this is something analogous to the Hardwicker's conjecture for the four color also.